Okay, decent amount of reading coming right up. Page 70 and 71 is 180 degrees Fahrenheit. So it contains 60 degrees Fahrenheit, brackets 180 degrees Fahrenheit minus 120 degrees Fahrenheit equals 60 degrees Fahrenheit, close brackets, of superheat. The condenser will first reduce the temperature of the discharge gas to the condensing temperature of 120 degrees Fahrenheit. Brackets. This process is referred to as desuperheating, close brackets. Then the condenser will condense the refrigerant to a liquid at 120 degrees Fahrenheit and will enter the expansion device at point A as a subcooled liquid at a temperature of 100 degrees Fahrenheit. Other conditions may be plotted on the pressure/enthalpy diagram. For example, suppose the head pressure of our R410A system increases. Keeping all other parameters of the system constant to clarify the concept, the new system plot is provided in figure 3.49. 3.49, a rise in system head pressure will result in a reduction of system capacity. With a new higher condensing temperature of 140 degrees Fahrenheit, brackets 539.1 psig or 553.8 psia, we see the percentage of liquid leaving the expansion valve to be about 64%, brackets 36% flash gas, close brackets, with a heat content of 63 BTUs per pound. Using the same heat content leaving the evaporator, 125 BTUs per pound, we have a net refrigeration effect of 62 BTUs per pound. This is a net reduction in refrigeration effect of about 13.9% from the original example. In addition, it can be seen that the compressor discharge temperature has increased from 180 degrees Fahrenheit to 200 degrees Fahrenheit. This example shows the importance of keeping systems properly maintained. Figure 3.50, an increase in suction line superheat results in an increase in compressor discharge temperature. Shows how increased suction line superheat affects the first system in figure 3.44. Flip back to 3.44. 3.44, a refrigeration cycle plotted as a pressure/enthalpy chart. The suction line has not been insulated and absorbs heat. Notice that the amount of sensible heat added to the refrigerant in the suction has increased, causing an increase in the temperature of the refrigerant entering the compressor. Notice the high discharge temperature, about 100 or 200 degrees Fahrenheit. This is approaching the temperature that will cause oil to break down and form acids in the system. The compressor must pump more refrigerant to accomplish the same refrigeration effect, and the condenser must reject more heat. Before its manufacturing phase-out date in 1996, R12 used to be a popular medium temperature application refrigerant. Environmental issues have caused manufacturers to explore some different refrigerants to replace R12, namely R134A and the newer refrigerant blends. R134A has a zero ozone depletion potential, but has oil compatibility problems and cannot be easily retrofitted into existing R12 systems. R134A also experiences a reduction in capacity when used in low temperature applications. Brackets. Environmental issues will be covered in Unit 9, Refrigerant and Oil Chemistry and Management, Recovery, Recycling, Reclaiming, and Retrofitting, close brackets. A medium temperature R134A system, figure 3.51, so 3.51, a medium temperature R134A refrigeration system showing operating temperatures and pressures. would plot out on the pressure enthalpy chart as follows. Use figure 3.52 to follow this example. 3.52 is on the next page. Yeah, it's a big pressure enthalpy diagram. An R134A pressure enthalpy diagram. We got pressure on the y-axis and enthalpy on the x-axis. Enthalpy as in BTUs per pound. One, refrigerant enters the expansion valve at point A at 105 degrees Fahrenheit, subcooled 10 degrees from 115 degrees Fahrenheit. 2. Refrigerant leaves the expansion valve at point B with a heat content of 47 BTUs per pound. The quality is 33% vapor with 67% liquid. It then travels through the evaporator. 3. Vapor refrigerant leaves the evaporator at point C with a heat content of 109 BTUs per pound and a net refrigeration effect of 62 BTUs per pound. Brackets 109 minus 47 equals 62. 4. The refrigerant enters the compressor at point D with a superheat of 40 degrees Fahrenheit and a heat content of 114 BTUs per pound. The vapor is compressed along the line from D to E. Note the lower discharge temperature at 160 degrees Fahrenheit. 5. The refrigerant leaves the compressor at point E with a heat content of 130 BTUs per pound. The HOC for this system is 16 BTUs per pound. I forget what HOC stands for. 6. The refrigerant is then de-superheated 45 degrees Fahrenheit from point E to the saturated vapor line. 7. The refrigerant is now gradually condensed from the saturated vapor line to the saturated liquid line at 15 degrees Fahrenheit. This is the latent heat of condensation being rejected. 8. The saturated liquid is now subcooled from the saturated liquid line to point A. It is subcooled 10 degrees, 115 degrees Fahrenheit minus 105 degrees Fahrenheit, until it enters the metering device at 105 degrees Fahrenheit. The process then repeats itself. As mentioned earlier, R502 was used primarily in medium and low temperature refrigeration applications. Its manufacture was banned in 1996. R502 is an azeotropic refrigerant blend with negligible temperature glide, and it behaves like a pure compound. R404A is its long-term replacement refrigerant and has a slightly higher working pressure than R502. Figure 3.53 Figure 3.53, an R404A low-temperature refrigeration system. It's a pressure enthalpy diagram. I think pressure is always on the y-axis. So yeah, figure 3.53 shows a low temperature refrigeration system plotted on a pressure enthalpy chart incorporating R404A as the refrigerant. The system is a commercial freezer operating with an evaporating temperature of minus 20 degrees Fahrenheit, brackets 16.7 psig, close brackets, and 115 degrees Fahrenheit, brackets 290 psig, close brackets, condensing temperature. Follow the sequence below. 1. The refrigerant enters the expansion valve at point A at 105 degrees Fahrenheit. Subcooled 10 degrees Fahrenheit from the 115 degrees Fahrenheit condensing temperature. 2. The refrigerant leaves the expansion valve at point B at minus 20 degrees Fahrenheit. 55% vapor and 45% liquid to be totally... Okay. That's it. Pages 70 and 71. See y'all tomorrow.